Today I will start with the part on link analysis. Before I proceed, I just wanted to tell you that there is still one thing I wanted to look at concerning classification, which has to do with the criteria that should guide your choosing of a classification tool, you know, classification algorithm. We have seen many classification algorithms. Which one should I use? Why should I prefer one over another one? Given that every classification tool is going to fail in some cases, that's life. So the question is, what does failure or success depend on? Okay, so in the next lecture, we are going to peek a little bit into that, just a little bit, to give you an idea. We will, in particular, consider, let's say, the KNN, a generic classifier, actually, and we will see what accuracy of, which factors affect accuracy of classification. I'm speaking of supervised classification, not clustering. So instead today we begin something new, which is going to take us some time, I think a couple of lectures at least, and which is a very important aspect of information retrieval. So for the web, link analysis means extracting information from the link structure of the web. We have not used this information at all, right? So far, for us, the web was a collection of documents, just like another one. But actually, the web comes with a hyperlink structure. So it is a graph, in fact, in which pages are the vertices and hyperlinks are the arcs. And it would be surprising if this structure were not providing us with precious information, right? It would be surprising. Also, some of the techniques we are going to look at in these and the coming lectures, they're actually part of a broader class of information retrieval and data mining problems, which collectively goes under the name link analysis, graph mining, if you want, and which finds application in other areas, not necessarily analysis of the web. It can be used in recommender systems, as well as in analyzing the structure of social networks, be there real social networks connecting humans according to some relationship, or online social networking platforms. Okay, so these tools are widely used in practice, with variants, of course. So it is a good idea to know the basics, at least. And of course, if you want to know the basics, where should you start from? You should start from our friend, the pageRank algorithm, which is one of the first effective users of link analysis to large-scale dimensions, datasets like the web. So, in this lecture, in the lectures on link analysis, I mean, you find the material in the book, in the Web Information Retrieval book. But I'm following a little bit the approach adopted in the other book I suggest, which is also freely available online, which is the book on massive datasets by Leskovec and friends, Ullman and... Because I think this part is better done, in my opinion, at least. No, it's not better done, actually. The perspective it takes is a bit more consistent with what we want to do in this course. Just that. Actually, these are both excellent books, in my opinion. So, it's often the case that you get graph data. Some cases are obvious. If you take Facebook, well, that's a social network. I mean, what does it mean, social network, in the end? It means that you have a huge graph where links have a meaning. In the Facebook graph, for example, normally links mean friendship relationships, okay? Nowadays, the Facebook interface has become increasingly complex, so sometimes you can consider these edges can come up with labels. For example, the level of visibility of your posts by other people. Okay? It's also important that you understand that sometimes the network is not explicit, as in this case, but you can define an implicit network on top of the data you have. For example, think of people liking items, for example. I issue a post and someone likes my post or not. Thumb up, thumb down. In that case, this also defines, in some sense, a relationship in which I will have, for example, I could decide that I have a relationship between two users whenever one user liked at least one post of the other user. You can come up with any other definition depending on the application at hand and on some sensible analysis of the problem at hand. Okay, so since now, remember, networks can come up in several forms. They can either be explicit, like in the relationship, in Facebook's relationship, or they can implicit. You find a network that actually there is some network structure on top of your data. For example, in other cases, it's hard to see, but these are political blocks. Colors reflect different attitudes towards a certain topic. For example, I'm just guessing now. Blue dots might represent conservative opinions, so people taking a conservative stance, red or whatever, might be liberal, let's say, and then you have a gray, or in this case, yellow or green area denoting people that actually can express both types of opinions. And what you may be interested in is, for example, studying the degree of connection between blocks reflecting different opinions. And you can understand, and you can come up with very interesting views. For example, you could identify what are called echo chambers. For example, the tendency of people to mostly read or being interested in points of views that are consistent with their own. Okay, so you can analyze a social network for other reasons than just making money. I mean, you can just conduct social experiments or let's say, social analysis on a large scale. Then, of course, you have information networks. And this is, for example, one case of a network which is derived from the data. For example, when I write an article, I normally cite other papers that are, in my opinion, relevant to the topic I'm studying. And if you think of it, if this is my paper, and this is the list of references, every reference can be regarded as a directed link, in this case, towards other papers. Then it is obvious that if you take a collection of papers, of articles, scientific articles, this will define a network where every link corresponds to a citation. Okay? Very simple. I mean, it's very easy to get a network. I don't want to say it's very easy as an exercise. I want to say that they naturally, spontaneously emerge from the data you have very often. Of course, communication networks, technological networks. Königsberg Bridge problem, you know? Can I go across all the areas, so visit all the nodes, so the corresponding network traversing every bridge exactly once? Sometimes, so the web. The web is a set of pages with hyperlinks. So far, this is the view of the web we had. They have contents, and then based on the contents, you try to find relevant web pages given for a certain query, for example. But actually, they come with hyperlinks, right? Pages point to each other. And the question is whether we can leverage this information in some way. Let's try. So given that the web can be viewed as as a graph, where nodes are web pages, or sometimes they are entire websites. Depends. You can define, you can have different levels of granularity. For example, nodes can be websites like www.diag.uniroma1.it, and then you can have links depending on whether at least one page from a website points to another page of another website. Maybe you add weights on the links reflecting how many times this happens. Given that you can do this, the question is why this should help you in some way. And this brings us to finding relevant documents, web pages, of interest to a given query. So I guess you were too young back at the time, but at the end of the 90s, people were confronted with this very problem. I mean, the web was still relatively in its infancy, so it was relatively small, millions of pages perhaps, but it was growing bigger and bigger at a very high pace. So, and the problem was organizing the information you had in the web. Organizing, I mean the following. Think of a world without web search engines. No Google, no DuckDuckGo, no Yahoo, nothing. So, try to think of the problems you have without a search engine. Today, I'm looking for something. What should I do? Well, I start with a page and I start crawling, trying to get closer to what I'm interested in, right? You can do this with, I don't know, 100,000 pages, perhaps, 1 million maybe, but eventually this becomes an insurmountable effort. So, of course, people realized this at some point, and eventually you had the birth of portals. For example, some were very famous. Of course, you would have portals associated to main media outlets or TV channels. And from those, you could begin your navigation, for example. Then very soon, you would start having directories of high-quality pages on different topics like DMODs or portals like Yahoo. And so this would be a good starting point. But in practice, you would have to organize, how should I say, this wealth of information at a local level as well. For example, you would keep bookmarks with the main websites to begin from for different topics, right? Which is at some point becomes a bit unmanageable. This is the problem also. There is a second problem. This was the first problem, just organizing information provided it is of good quality. But then there is the problem that actually the web is not a collection of scientific papers. Especially nowadays, let's say that I'm just throwing random numbers there. You find a lot of bullshit, let's put it this way, let's be honest. But at the same time, it is still true, it was true, and it is still true that you find huge amounts of very, very rich and valuable information. It is there, it is buried there. If you can look for it, if you can find it. Actually, it contains very high quality information on virtually every aspect of life. I'm not just speaking of Wikipedia. I mean, of course, Wikipedia is an example, but it's easily accessible. You know it is there and you can access it. But I'm speaking of other things you don't even know are there, but could be very relevant and high quality material for the search intent you have at any given moment. So how do you find them? It's like sometimes without a search engine, it's like finding a needle in a haystack. At some point, eventually, you started having the first search engines as the ones we know. You know, relevant pages based on the contents of a page, textual content, metadata, and so on. You would start having at least the opportunity to retrieve documents that were relevant for a given query. So at least they were probably speaking about something related to what you were looking for. But relevance is not the same as quality. We already said that. So you would still have a random list of documents in which perhaps the highest ranking document was one just full up was a spam page full of repetitions of one word appearing in your query. People used to do that. It was called cloaking. For example, you repeat, let's suppose that you have a website in which, I don't know, you are selling shoes, and you want to maximize your ranking for search engines that just blindly use the frequency with which words appear in a given document. Words of a query appear in a given document. What you might try to do, for example, is to repeat the word shoe, I don't know, 1,000 times in the main body of your page, or perhaps in the title or main body, I mean in key points of your document, but just with the same color as the big background. So the page looks nice, but actually the page is a spam. So it is trying to maliciously increase its ranking on a textual-based search engine. And this would happen very often. So how do you try to combat this? How do you try to distill quality of documents? Well, actually, you can start making a couple of simple observations. Very often you begin with very, very simple observations. I mean, little more than common sense. For example, yeah, we have many sources of information, but which ones should I trust? Which ones are more valuable? Which ones, irrespectively of what the opinion on a given topic is, which information sources have high quality, represent high quality material with respect to a topic I'm interested in? For example, one might observe that very often trustworthy information sources may tend to link to equally trustworthy ones. You see what I mean? For example, if you are the website of a prominent newspaper, regardless of opinions of the newspaper, if it is a highly cited, well-respected newspaper, I don't know, let's say the New York Times, Wall Street Journal, Le Monde, and so on, it's unlikely that it will have, let's say, a link pointing to some crappy conspiracy theory website, right? You don't do that. I mean, your reputation will diminish. A lot of your readers will realize that and punish you severely for that. So this brings to the first, let's say, heuristic observation, which is maybe it's more likely that a trustworthy web page points to higher quality ones in average. Not always. Maybe sometimes you just you do something clumsy as a journalist, but most of the times this is likely to happen. Also, there is some. If you want to have, let's say, more pointers to pages that are related to news or newspapers, perhaps a good starting point is to begin with newspaper pages you know about, right? Actually, this was already in the old idea of portals, but this is another reasonable trick to try. So, what is actually connecting all this stuff? Actually, all these very simple observations are suggesting to us that looking at the link structure might actually be a good idea. For example, let's consider a stupid example. Let's assume that for some reason, maybe related to some news, to some recent piece of news, I have that one website, one page is is linked to by a number of authoritative newspapers pages. So if I don't know anything about this page, I might be induced to think that at least for this topic, this page might be authoritative. Authoritative in the sense that the quality of the contents it provides is not that stupid. Actually, there is a number of such pages that perhaps correspond to less known magazines that are actually high quality. in the sense that, for example, they do a lot of investigative journalism. So the generic idea behind is, well, actually, not all web pages are as important. I mean, some are more important than others in the sense that they are more authoritative in the way I was saying before. For example, at the first sight, it might appear that a very simple heuristic to decide how important a page is, how authoritative it may be, is reflected by how often it is pointed to by other pages. For example, I look at the snapshot of the web graph, and I might be tempted to say like this, this page is authoritative, right? You see that? Actually, this way of ranking pages with respect to authoritativeness is not new. This is also was already used in bibliometry, and actually it is still used today. If you want to, nowadays, the most widespread way of deciding whether or not a publication is important is just to count the number of citations to that publication, which means sensible. I mean, it means, looks like a sensible approach. Actually, it has a number of drawbacks. For example, some communities are larger than others, and their papers have an average number of citations which is larger. So if you start comparing apples and pears, perhaps just using one single parameter, maybe you may get biased answers. But in principle, it has some sense. Okay, so in web graph jargon, this is normally referred to as in degree. Directed network, number of points linking to a page in degree of a node. Okay, this is one first way. But actually, over time, people have come up with more sophisticated solutions or algorithms, indices, and they correspond to a number of the topics we are going to see here. For example, the pageRank algorithm, the hubs and authorities algorithm, which is known as HITS, and actually is actually very nice. It is almost contemporary as pageRank, but it was less successful for reasons that I will mention further. It's actually used in at least one web search engine called Salsa, but it is not the most widespread. Then we will show how actually these ideas can be used to profile, let's say, information from users, profile information about users. For example, which pages users navigate more often can be used to rank web pages with respect to the interests of the users, which is very important. It's called personalization, and is one of the key ingredients, was one of the key ingredients at the beginning of online advertising on web search engine pages. Okay, so it's a very important aspect. And finally, we are going to take a peek into how you can use link structure of the web to identify possible spamming activity in the web. Okay, so pages, identifying pages that have low quality but might be ranked high by a search engine just because they're cheating. So, what is the basic idea? The idea behind pageRank, and also behind InDegree actually, is that every link is like a vote. Why do let's suppose for a moment that I am not cheating, so I'm not artificially linking to a page because I want to boost that page's rank. Let's say I'm honest. I'm writing a website, I'm designing a website, and I want to add links, outlinks to other pages that I think might be of interest for the topics I discuss in my website. In that case, it is not too naive to think of every hyperlink as a vote. The question is, why am I adding a hyperlink to a given page? The reason is that I think that page is interesting with respect to the topics I'm interested in, right? So you can consider every hyperlink into one page as a vote. The in-degree, so taking the maximum in-degree as a ranking criterion, stops at this point. So every page is a vote, and I count the number of incoming votes for every page, and I rank pages accordingly. Other algorithms, such as pageRank, actually take this a step further. So, for example, in this case, they will not just, an algorithm like pageRank will not just count the number of incoming links, but it will also weight every incoming link with the score of the pages that is pointing to it. Okay? So this is sort of a recursive definition. So, for example, if by any criterion I have given a very high score to the New York Times, every vote the New York Times gives through its outgoing links weighs more than a link coming from another page like lb.com, where lb stands for lucabecchetti.com. Okay? Let's say any page from me will be every link coming from my personal web page will have a lower rank, probably. Let's take this picture, which is useful. You don't see the numbers very well, but let's say that the radius of the balls reflects their score, according to some criterion. Let's say PageRank. Now, what happens is that, for example, why does this page correspond to a very big ball? Well, the reason is that it is pointed to by other important pages mostly. Of course, also by smaller pages. But for example, this page is pointed by these medium-sized balls, but not by the bigger balls. That's why its PageRank score is a bit lower. Okay? Instead, these two balls are pointing to each other, and they are pointed to by virtually all the medium and small-sized balls. That's why their PageRank score is so high. Okay? So now you have two double criterion. One has to do with the number of links that point to one page. Another one has to do with the importance of the pages whose links point to another web page. So you have to combine these two ingredients to get together. How do you do this? Huh? Let's try to do this. Okay, I will remind me that I have to tell you something at some point about a convention. But it is too early yet. So, when you start reflecting about these things, you have to begin from some way. Now, in some way, let's say that you have an intuition. Let's try to play Breen and Page, sitting there writing their PhD thesis and trying to use this idea. They knew the literature about bibliometry, and they had come up with this intuition, actually not just them, but also their advisor, Rajiv Motwani. So they had this intuition that actually you should consider both the intrinsic importance of pages and the links into account, and you try to combine this stuff. Then at some point you sit there and you say, okay, I don't know how I'm going to compute these quantities. So the RJ is the score of the page. I don't know how I'm going to compute it. I will, perhaps. But let's assume that I have the scores, okay? Then, how should the score of one page be defined in terms of the score of the other pages? Is the question clear? For example, let's take this page. How is the score of this page defined? First of all, if every incoming link is a vote, I am only considering the pages that have links pointing to J, right? And these would be I and K. I and K. On top of that, I am considering, so if my rank is I, what should I do? In a way, the rank of it, you can think of the rank of a page as a certain budget of votes that you can give to other pages. But you should not be allowed to use your budget for all the pages in the web. You understand what I mean? So this, in some sense, recognizes the fact that you, first of all, you cannot point to each page in the web. You have to make a choice. And likely you're going to point to pages that you find more interesting. On the other hand, this also reflects the fact that if I, for example, am pointing to 3 other pages, there is, maybe I like one page more than others. But the moment I put my, the moment I decide which my outgoing hyperlinks are, there is no way to discriminate which page for me is more important than the others. So in that sense, one easy heuristic, an easy model is to assume that my budget of reputation is split equally among the outgoing links, among the pages I'm pointing to. Is that clear? So if that is the case, then I could say that the rank, so the score of J, is what? The incoming score from I, which is equal to the reputation of I divided by the number of outgoing links, and here I have 3 outgoing links, plus the reputation, the score of K, divided by the number of outgoing links, which are 4 in this case, right? You see that? So, of course, this is a mathematical model. I'm not saying this is reality. Only, it turns out that this mathematical model is very effective. So it made the difference between Google and the other search engines that were existing at the time when Google came out. Okay, so it captures something important, okay? Even if though it is not probably the best description of reality we may come up with. Now, that's an interesting model also, because this model is, in a sense, a flow model. You know network flows, right? Huh? So in some sense, this model is sort of a network flow model in which you have balanced condition at every node. In particular, the incoming flow is equal to the outgoing flow, to the appropriate fraction of outgoing flow from every neighbor. Okay? So this is sort of balance equations for every vertex. The amount of incoming flow is equal to the amount of outgoing flow. You could also write that. Okay? So these are actually flow equations. They also have another interesting property. If you look at every link is assigned a weight equal to the number of outgoing links. So 1 divided 4 in this case, 1 divided 3 in this case. You see that? So in a sense, the amount of flow from I to J is equal to the total budget available at I on a link multiplied by the weight of the link from I to J, which is equal for all the links, for all the links. So the sum of the weights, how much is it? If I take one vertex, the sum of the weights associated to the associated vertices, how much is it? 1. Huh? So whenever you have a sum of non-negative numbers that sum to 1, that stinks of probability, right? Actually, it can be viewed as a probability. Let's remember this. Okay? So, let us see where this takes. Notice that we didn't yet find a way. So far, we have no way of finding the weights. So the RJs, right? We just know that if we define the weights in a, how should I say, in a recursive way in terms of each other, they have to satisfy these equations. We don't know yet how we are going to actually compute the weights, if it is possible, when it is possible. Okay, we don't know. We don't know this. We are just playing a little bit. So, what can I say then? Do you agree with this equation here? Ij means a link going from I to J. So, if I want to know which is the score of J, given the scores of pages pointing to J, I just sum for every page pointing to J, its score divided by the out degree. The I is the out degree of page I. Okay? You see that? You need 30 seconds to digest this or not? If anything is unclear so far, please stop me. Okay? Yes or no? Is everything clear so far? Okay. What is unclear? My arbitrary definitions. So some of you might be asking, what is the point of this? Why did I write down these equations? This is a mathematical model. So it is a model that at some point, Breen, Page, other people studying these things, they thought it was capturing something important. So in a way, the model is suggested by some intuition, but once the model is given, you accept it and try to understand how it works. So the model works in the following way. It assumes that in some way we will define weights associated to every node, positive weights, or at least non-negative weights associated to every node. And then we impose that the weight associated to every node, which is a measure of the reputation of the node, can be used to vote for other nodes that we are pointing. Okay? So the question at that point is, if I'm a node I with a given score, with a given authority score Ri, how is my score being split between the other vertices I'm pointing to? In this model, it is equally split. Okay? You can come up with other models in which the split is not equal. It's uneven, depending on weights associated to the edges. Many of the things we are going to say work also in that model, but very often when you have a graph, when you have a web graph, it's not easy to compute weights associated to the hyperlinks. Okay? So to begin with, no weights. In that case, the reputation of a node is equally split among its neighbors. Okay? Is that clear? Good. If this is the case, these are equations that describe how the reputation, the ranking, or the ranking score, the score of a document depends on the scores of the documents that point to it. Okay? Just to make you an example, when we said the in-degree, in the in-degree case, the model would be simpler. The model Rj do you agree with this? The in-degree, we were counting just the number of votes. This is another model. In that model, it's simple. The ranking, the score of a document is just the number of incoming links. This is another model. This is a different one. Okay? In this case, the score of a document depends on the score of other documents in this way. My score is equal to the score of any document pointing to me divided by the out degree of that vertex. Look at this example and tell me if the equations make sense. This is a practical example. Take a look. Do they make sense? Yeah? Okay. Now, can I compute these scores given these equations? Analysis 1. Yes or no? Yes. Okay. Which is the solution? Be careful. You have 3 equations, 3 unknowns. Have you got any constants? It's a homogeneous system, so 3 equations in 3 unknowns. You know homogeneous systems. You find infinite solutions, right? Oh, how can I do that? Well, you could add the following constraint or any other similar constraint, but this is the one normally used. Okay? You say all the scores have to sum to 1, which means that if you have a higher score, someone else is going to have a lower score. So it's a competitive setting in which you cannot have your score if not at the expense of someone else. So I have a higher score than you because I'm more authoritative, okay? If you add a further constraint like this, you can try to solve this system. Solving just this system gives you infinite solutions in which every value Ry, A, Rm is defined up to a common constant. Using that, the sum allows you to normalize and find a solution, okay? Is it clear? At least in principle. Why? Because you know, from analysis 1, that not always are you able to solve a system, a linear system, right? Sometimes you fail. You know the rank of the matrix, you remember? The rank of the coefficient matrix, the rank of the full matrix, including constants and so on. You can solve a homogeneous system if the coefficient matrix has no full rank, which actually, incredibly, is what happens in our case. Normally, let's say in all the cases we like, this matrix, you know which will be the rank of this matrix? n minus 1, where n is the number of unknowns. Plus that, you are done. Okay? But we'll come to that. Anyway, if you define this equal, what we have come up to so far is that if you use this model, this is a model of how importance of a page is decided. This is a mathematical characterization, a mathematical model of how pages, web pages, get their importance, right? It's a mathematical model. You can come up with a nonlinear model, a cubic model if you want. This is a very simple one. If you have this model plus a normalization equation, you can hope to compute a solution. So you can give every page a score, okay? It's a static score that only depends on the graph and on nothing else. You remember that at some point we were speaking of static scores? Yeah, this is an example of a static score. So, that's easy. We are done. PageRank. Almost. So life is not too easy. Actually, this is the very first type of model Brin and Page were thinking of. Then they tried to solve it, and they noticed that sometimes things were working just fine. So you were able to assign scores to pages, and apparently the scores seem to be correlated with the quality of the pages. Sometimes it failed miserably. For example, you would have one page that would get all the score, and all other pages would get 0 score, which is something you don't like that much. Okay? So you try to make sense. Why is this happening? In order to understand when this is doing a good job and when not, you have to adopt a different perspective. You have to look at this system as something else, and then you will understand. Okay? Is everything clear so far? Good. So, if you work out this example, this particular example, and you add this, let's say, normalization condition, you get these values. Okay? For example, this is telling you that Y and A are far more important than M. Let's see what it means. Let's go back to the network. Y and A are more important than M. What do they have so special? So, M, the poor M is just pointed to by A. Y is cheating a little bit. It's pointing to itself. It's artificially increasing its importance. Okay, so it's trying to cheat a bit, so adding more links to itself. Let's say actually A is genuinely important, it's central. Actually it's getting support from both Y and M. So let's say that the 2/5 of A is perhaps a bit more honest assessment than 2/5 for Y. Okay, this is an interesting point. It provides us with a bit more intuition. So How do I solve this system? Well, of course, you can use Gaussian elimination, all methods that you saw, you know, pivot, that stuff that you were using in your first year of university. Yeah, this bold eye, trembling, terror. Okay, you can do that by hand. That's not what you want to do when you actually have a matrix in which every unknown corresponds to a vertex in the web graph. Okay, because in that case, you will have billions of equations with billions of unknowns. That's not something you want to do with Gaussian elimination. What can I do? No Gaussian elimination. I'm going to compute that. Well, you can try to compute that because you can go one step back and look at these equations. These equations are very interesting. I mean, look at this equation. Let's say that J is the node you're interested in. Okay? Yeah? Just a sec. Because now we are approaching the point where I have to say that I'm using a slightly different convention than the slides. You see that? Sorry. Don't take notes for the moment until it's stabilized, okay? So let's put a 1. Let's put a 1 here. If there is one link from n to j. So a_n1 is 1 if there is one link pointing from n to 1. a11 is a1j is 1 if there is one link from node 1 to node j and so on. Okay? So I am assuming that n is the number of vertices. It's the same equation. This and that equation are the same. Okay? Whenever, why? Because whenever there is no link from I to j, this will be 0, right? And then you have this equation. Okay? Why did I write it like this? What do you think? What is A? A is a matrix, right? Okay? A is a matrix. And what this matrix is telling us is that actually this is a vector matrix multiplication. So if I define this vector, I put a t because it is a row vector. Normally, this is a convention. When you write just a vector, you mean a column vector. Most of the times. Okay? Hey, are you following me? Yes. Good. So to write that it is a row vector, I will put a T, which stands for transpose. Okay? So if this is my vector, then how can I write this equation for all the components at the same time? Okay? So in order to compute Rj, what I have to do is look at this equation. I am multiplying this vector by this column. You see that? You see that I'm doing that? So that's actually what I'm doing. Okay? Think of it. Think of the component j. What is component j of this vector? You take the vector and you multiply it by the column j of this matrix, which is this. Yeah? Do you see that? Take 1 minute. I know, linear algebra, maybe many of you hated linear algebra in their first year. Yeah, I'm sorry to inform you that actually linear algebra is widespread in information retrieval, data mining, all this stuff. And actually it's really used. I'm not kidding. It's really, really used. Okay, you can try to solve these data mining problems using more or less reasonable heuristics, but you will not really find, most of the times you will not really find real information inside the data. When you want to find something really serious, you're going to use very often linear algebra or even extensions, nonlinear extensions like what you do in deep learning, right? Where you have algebra but nonlinear. Okay? So please become convinced that this is equivalent to this. Okay? Yes or no? Now, let us take another look at this matrix. So if I I've been considering this matrix and dividing it by the out degree of the vertex, right? Of course. Sorry, people. You are right. You didn't get this. It's my mistake. I realize it now. Sorry. Now you get it. Yeah? It was, sorry, my bad. Okay? Is it clear now? Good. Yeah? Now, so this is 1 when you have a link, and 0 otherwise, right? How much is this? If you think about the network, the answer is very simple. You already know the answer. So I am dividing by the total number of outlinks from me to other vertices. It's 1. Yeah? It's always 1. Why? Because this is telling where your outlinks go. Okay? Is it clear? So, why am I doing all this mess? Because I like to torture you? Yes, I like to torture you, of course. But actually, there is a deeper reason for doing this. It's a different way of looking at the problem, of looking at what you are doing, and trying to make sense on how you should go, where you should go from here. That's the reason why I'm doing this. So I'm changing perspective. Before, we have seen at these equations just like a flow problem. It's a flow problem. Now I want to change the perspective, and in doing so, I will be able to, for example, give explicit conditions under which you can solve this system. I will be able to say when you can solve this system, and how you can try to change it a little bit if you are not able to solve it. Okay? I'm more or less doing what Brin and Page did, essentially. They didn't come up with a full-fledged solution of pageRank like this. Otherwise, you look at the pageRank algorithm, you say, what is it doing? Why? We want to understand why it does what it does. So, are you still with me? Good. Yes?
Get why R transpose is equal to R transpose times M.
Why? Mij is equal to AI.
R transpose is equal to R transpose times
Ah, okay. This is just this equation written in a compact way.
So the first term is
M is defined like this. So Mij is exactly equal to this. So from now I can write Mij, right? Now, let's think of, look at this equation and tell me how do I compute from the, if I look at this equation, how do I compute the jth component of this equation? I have to take the jth component of this equation is equal to this row vector multiplied by the jth column of the matrix. It's a vector matrix multiplication. You see that? Is it clear in this way? The jth component here is equal to the vector multiplied the inner product between the vector and the jth column of the matrix. It's linear algebra. I mean,
R transpose with J above J.
no, you cannot transpose. J is just the jth entry of a row vector. I mean, if you want, I can call this Q, if you like it more. I put the T just because otherwise for me it's a column vector. But actually we are computing a row vector here. Okay? Is it clear now? Be honest. It's convenient for you, not for me. For me it's just spending more time. For you it's actually, this is the part you have to understand. All the rest, I mean, follows. But this part you have to understand. I mean, how you do the vector matrix multiplication should be clear to you. Normally you see matrix vector multiplications, right? Yeah, now you will also see a matrix vector. This is actually a matrix vector multiplication. Only the vector is on the left. So what's wrong, people? Yes?
For me, it's just why I'm not so sure to understand why we have the notation like R transpose is equal to R transpose times M.
Okay. It's not clear that this is going to happen. I'm just saying, assume that I have this equation. These are these equations, right? I'm just writing these equations in matrix form, nothing more. I'm not saying that those equations are true. in some cases, you cannot solve the equations. I'm not saying that we are solving the equations. I'm saying assume that we have solved the equations. Can we find, this is just the matrix, equivalent of writing this for every j. If I write this for every j, this is equivalent to writing this. I'm not saying anything more than this. So this is an equation. Then there is the question, as you correctly say, when does the equation admit a solution? Yes, we don't know yet. We know in general this is a homogeneous system. And in general, this equation might admit an infinite number of solutions. And that's why normally I say I'm looking for all solutions such that this is 1, sums to 1. If I add this, then I can find a solution, perhaps. It's not sure, but if I don't add this, I will not have a unique solution. I will have infinite solutions. OK? What's wrong there?
Can you please explain why the sum of them is 1?
OK, that I can do.
Thanks.
Of course. Can I cancel this picture now? So let's try to see what is MAM in this case. Actually, what is Mij? Yeah, that's my definition. Look at the picture. 1 divided what? The number of outgoing links. So the weight on this link is 1 over di, 1 over di, 1 over di, right? When I sum all the sigma, all the Mij's, what am I doing? I am summing this, right? Yes. Correct? Now you get it?
Yes.
How many A's, how many of these entries are 1? Exactly di.
1, yes.
So if you want to look at it in a different way, which is the one I want to you become acquainted with, you are weighting these outgoing links with equal probabilities, 1 over di, and you are summing the probabilities. So the sum has to be 1. If you want to look at it in a different way, it's the following. Assume that I have some walker. You know, a walker? Someone walks. And whenever the walker is at any given node, she will go to any of the outgoing neighbors with the same probability. Right? What is the probability of going to some neighbor? It is 1, because it will go out. What is the probability of going to one specific neighbor? 1 over the number of neighbors. So we are coming to the probabilistic interpretation that is actually the one that will help us understand how to solve this problem, when it can be solved, and how we can fix it, change it a little bit to always be able to solve it. Okay, let me see how much time I took from you. Today I would like to stop. I will stop in a few minutes so that you take your. You look surprised. You look troubled. Come on, open yourself with me now.
I was thinking at the product.
RT equal to RTM.
Yeah, I have just one doubt.
It's the adjacency matrix.
Ah, okay. It's a matrix. So.
Of course.
Okay.
It's a matrix. Yeah. I, it's an n times n matrix. It's the adjacency matrix. Notice that this matrix in general is not symmetric because the graph is directed. Okay? It's not an undirected graph. It's not necessarily a symmetric matrix.
We have like zeros and one in the A matrix.
Only have zeros and ones in the A matrix. Absolutely. Adjacency matrix. You know? Yeah. Adjacency matrix, first year of fun. That's it. You never thought you would use it. Instead, you will. Because, you know, whenever there is a matrix, there is linear algebra. So, and you can do a lot of stuff with linear algebra. So there is also, now, is M clear? Is M clear now? Because that's another matrix, which is called transition matrix, and which has another meaning, which is also very interesting. So please tell me if you are OK now with every and each aspect that we were dealing with. Good. Now, normally in 90%, when not 95% of the papers and literature you consider in this topic, this is the way you write this equation. In these slides, and 5% of the people, sometimes they write it like this. They take the transpose. If you take the transpose, you will have, yeah? It's the same equation. You know, it's a matrix. You just rotate everything 90 degrees, just to be clear. It is the same equation. Only this time, this is a column vector, and this is a square matrix again. So in this case, the sum, of course, is equal to 1. Which means the ith row of matrix M is sums to 1. If you write it like this, it means that the column, the ith column of matrix MT sums to 1. Okay? But it is, nothing changes. Only you consider right vectors, right column vectors, or left row vectors. It's the same. Normally, I wouldn't make this precise clear, because it's pretty obvious. But since in these slides, for some reason, they're using this notation, I stick to it. Then you could ask, why are you changing it? I mean, why bother? Because most of your life, you will find the equation written in this way. So I will go over the slides, but trying to stick to this convention. But it's important that you're aware of them, of the convention. Okay? So this is called a stochastic matrix. When all the rows of a matrix sum to 1, or all the columns, depends on the matrix, is called row or column stochastic. Okay? So the rows have a meaning of probabilities. If they have a meaning of probability, they must have a meaning, right? If they are probabilities, they are describing some stochastic process. Which kind of process? What do you think? Have you ever seen a stochastic matrix in your life? Come on, I'm pretty sure you have, in some other course. You remember of anything which is described by a matrix with rows summing to 1 or columns summing to 1? Anything? Ring a bell?
MDP.
M what?
MDP is
M?
MDP. Yeah.
M?
MDP.
M, Markov decision process.
Yeah.
Markov chains. Yes? Markov chains. Yeah. That's exactly what these equations actually are describing a Markov chain. You can look at them as a Markov chain. You change the interpretation. Then we have to understand, what does it mean? Looking at this like a Markov chain, what's the meaning? We will see this in the next half of this lecture. And we will try to see why this is helping us a lot to kill this guy, which is otherwise resisting us. Okay? Okay, I'll see you in some 15 minutes from now.